Welcome to this IET Mersey and Western Cheshire Local Network Energy and Environment Group webinar. I am Rob MacDonald. I am the chair of the Merseyside and Western Cheshire Local Network and our Energy and Environment Group. I will be the host for this evening's webinar. This webinar is the first of 6 webinars the Merseyside and Western Cheshire Local Network has organised between now and the end of November on a range of subjects, so please look out for our upcoming webinars. This evening's speaker is Mr. Tom Woods. Tom is the Technical Manager for Suez Recycling and Recovery Limited. Tom is a member of the IET and a Chartered Engineer. Tom's lecture will address the latest developments in creating energy from household waste that cannot be recycled. During the webinar, you can ask a question. Tom will answer the questions at the end of the presentation, and I will do my best to consolidate questions on a common theme. I hope you enjoy this evening's presentation.
Good evening, everybody. Hope you can all hear me okay, see my screen okay. This is a lecture I gave to the IET in person last year, the end of last year, and hopefully it will translate well into a webinar. As you can see, it's the latest developments in energy from waste, so hopefully in the question and answer session at the end I can answer all your questions and we can discuss how the waste industry is moving forward. And without further ado, we'll start. So this presentation will be 6 basic parts: a quick introduction, an overview of Suez Recycling and Recovery UK. We'll look at what energy from waste is, or what it can be at the minute. We will look at what assets Suez has in the UK. We'll look at the latest developments in energy from waste, as is the title of this presentation. We'll have a look at where we think it's going, and I'll have a Q&A at the end. So if you can just all, as we said, put the questions in the Q&A thing and we will pick some out at the end and we will answer them. So just a bit about me. I'm Technical Manager Engineering at Suez, at the energy side of Suez R&R UK. I've Masters in Durham University, graduating in 2009. I went straight into the power industry, RWM power scheme. I was brought into CETA as it was then, which was later became Suez. It's just a rebranding, same company. I was the first electrical engineer taken on in the UK, and I think the fact that happened is probably going to feed into my lecture in terms of how the waste industry has moved in less than, just under 10 years, how it's moved towards a processing industry away from being about collection of waste, or purely collection of waste. I was appointed Senior Electrical Engineer in 2015, and I'm now seconded as Technical Manager Engineering. So I actually got my chartership in 2018, so it doesn't seem that long ago now. It was 2 years ago. So I was chartered with the IET. I was went to Manchester for that. That was good fun. My day-to-day duties, you can see below. I won't read them all out, but it looks at some of the more technical sides of our business, and especially the energy side of the business. My specialty, as you can see from my brief CV, is HV, so it's high voltage switching, high voltage rules. Suez Recycling and Recovery UK, a few key figures. 5,000 people around the UK and 10 million tons of waste. So you can see the sort of scale of involved just in the UK. We were established in 1988 by our French parent company as CETA. As briefly mentioned before, we had a name change towards Suez. Our goal is to create the circular economy, which I know is a hot topic at the minute with the circular economy package. Was out in the EU in the last couple of years, and it's generally it's quite an in concept at the minute. So we're looking to give waste materials a second life, reuse, recycle, recovered for energy content. And the last bit is where I sit in that circle. That's what we're going to be talking about today, the recovery for the energy content. Brief look at the figures of the company. I think I will pick out some key ones based on this this lecture. So we've got, in terms of our energy recovery, we have 8 energy from waste facilities. That's the mainstay of my work in the group anyway. We have operating landfill sites, we've got closed landfill sites, they have some energy recovery as well in terms of gas combustion. We also have a number of other sites which are using more novel techniques, which I'll discuss later, to recover energy from waste. I think one of the key figures down there is the amount of megawatt hours we generate, both from our landfill gas engines and from our energy from waste facilities. And when I started with this company, it was more than flipped the other way around, and we were mostly recovering energy from landfill gas. Now we are mostly recovering energy from waste plants, and that's only carrying on the other way. That is, as this 2016 figures, so that will be significantly the other way now. As I discussed, the circular economy is the guiding principle of Suez. You can see the various parts of the manufacturing cycle, the economic cycle here. The bit where things come out as waste is what we are trying to cut down on, and that's traditionally what Suez, or CETA as it was, did. It collected waste, it threw it in the ground, and that was really the business. And now obviously we're looking to do things a lot more intelligently, a lot more sustainably, I think is the key. So the part of the company I mainly sit in is this part here, where it's the recover, so the energy from waste. So we're looking to recover the energy from the residual waste that can't be recycled. I mentioned that we have a French parent company, which Suez. We originally started CETA with Suez. This is just to give you an idea of the global scale of that business. It's waste and water. Obviously, I work on the waste side, and we talk about waste today. We see we can have a substantial water business as well. Yeah, we're based in Paris, a large multinational company. A couple more key figures. I think we've had some of these on previous slide, but yeah, you can sort of get a scale of the amount of tonnage we handle through our facilities each year. Now, this is a slide I have touched on a second ago, but I think this really does illustrate the change both in Suez and in the waste industry in general in the UK. If you can see, it was only 2009 this graph started, so it's not that long ago really in the grand scheme of things. And you can see the high percentage of landfill our business was then. It was obviously just before I started the company. We're looking at 90% of our business being landfill, potentially a bit more, as you see from that graph. As we get forward, you can see a very, very rapid increase of energy from waste. Very rapid increase of energy from waste, very rapid increase of alternative fuels in our mix, and also obviously the recycling. So this is a projection. It's currently based on 2017 figures, but as you can see, we've got continued to grow in the energy from waste side, and the landfill does continue to fall. So I mentioned it in passing, but municipal solid waste, that's MSW. So that is your general black bag waste, as it were. That's what you produce domestically. It's what you put in the bin. It's everything that you don't put in the recycling bin, or if you do have it, food waste bin. You can see this is a typical composition of what we get through. I'm not sure what site this is from, but there is a surprising amount of regional variation in the different sites we have around the country, which is interesting. But you can see here that we have like paper and card and things. We have plastics, we have garden. Food waste is one that some areas of the country do collect and recycle, some don't. And you can see, I think what I want you to take from this slide is it's a mix of stuff. It's heterogeneous waste, and if we try and use it as fuel, it's a heterogeneous fuel. And this slide just sort of illustrates where we are in terms of Europe. I think something that's often levelled at energy from waste processes, or an argument often made against them, is that bringing energy from waste processes in will reduce recycling rates. Now, I think this chart illustrates quite well that that tends not to be the case, and higher recycling and higher energy recovery do go hand in hand. You can see the countries that have virtually no landfill all have high levels of incineration, as it's called here, energy recovery. The countries which landfill tend to landfill a lot, and they don't have high recycling rates. So we like to see energy recovery and recycling as part of the same tool. It's something that goes hand in hand. So the energy from waste process. Let's start the process, which is combustion. It's a thermal process. You are burning the residual waste. It's direct in most cases. So the majority of our sites have a moving grate, which we'll show some pictures of later. This is the industry standard method. This is what generally happens around Europe and around the world. There's 4 stages on the grate. You have drying, where the water is driven off, the sensible water content. We then have vaporizing, where it's starting to heat up and releasing gases. They then oxidize, which is the complete combustion, and burnout removes any residuals that haven't been burnt haven't broken down in the first 3 grates. The furnace with the grate is then immediately above it, so it goes up into a water tube boiler to start to extract the energy from it. We have later stages I'll come to later, but it's around 4 hours from the waste going into the hopper at the start of the process to being completely incinerated. We tend to get around 0.56 to 0.6 megawatts as generated electrical power per ton of waste processed. So you can see you can get fairly significant amounts of waste, amounts of power from the waste. Tees Valley, one of our older facilities up in the northeast, provides enough electricity for 100,000 homes. So to go into the technicalities of the actual what's in the fuel, I know we saw a brief overview in terms of what it is, in terms of what people put in the bin, but you get things in the fuel such as a moisture content, you get an ash, you get various potential pollutants, so you get chlorine, sulfur, things that could potentially cause us trouble when we burn them if we don't burn in the correct way and treat the residual gases that come through. Obviously, we also end up with potential operational issues with combustion not being perfect. We're not burning coal, we're not burning gas, we don't know what's in there, and we have to deal with that. Very quick combustion basis. I think a lot of people are aware of combustion triangle, heat, fuel, air. The majority of what we are combusting in this process is carbon, so CO2 and heat. Heat's recovered in the form of steam being raised, and then that's passed through a steam turbine. You can see on this this chart where we try and aim the combustion process. We want tiny bit of excess air compared to the fuel. This gives us a high efficiency, and obviously we want to keep the CO content to an absolute minimum as a pollutant. It's a balance. We have to balance the various parameters in our equation to keep the efficiency high and to keep pollutants low. Obviously, when you look at this, you have to, of course, again remember that this isn't a uniform fuel. It's a fuel that constantly varies. It's a fuel that we don't know what's going to come in, not even 1 hour to the next, let alone 1 day to the next. And you can see a typical, a very nice little schematic of a typical energy from waste site. You can see your bin lorry, your tipping truck tips into the waste pit. Now, this is where we try and make the fuel as uniform as possible. There's a lot of mixing we do with cranes. There's a lot of skilled operators that go into sort of making this, so each grab of this crane, it has a uniform amount of fuel, uniform type of fuel, should we say, as possible. Once this is mixed, this goes into the hopper. I think I just mentioned the grate, so it comes down here onto the grate. Let's say it's a moving grate, it combusts here in the 4 zones. All the heat moves upwards and is extracted by this boiler. The boiler continues up through the pass and all the way around the process, comes out the other end, is treated by our flue gas treatment system, and then is pulled through by the ID fan up the stack. The energy that's extracted, as I mentioned, is in the form of steam. That is sent to the turbine. Turbine drives the generator, and energy is recovered. And you can see sort of a very rough mass balance of the process. The APCR is pollution control, air pollution control residue, so that's what's taken out of the system by our scrubbers, essentially. So that's taken out as a solid out the system. It doesn't go up the stack. It's safe. It's contained. The IBA is bottom ash, so that is things that are the solids. It's solid ash. That's taken. We recover ferrous metals, recover non-ferrous metals, and the rest is sent to aggregate. So, as you can see from all this process, we do keep circular economy going. We reuse as much as we possibly can in the whole process. And as I said, energy from waste, the key bit is this electricity. I mentioned before the moving grate. Hopefully this gives you some idea of the scale of the process, some idea of how the process actually looks in reality. You can see the gentleman stood there, so it gives you a bit of scale of how big these things are. So they are fairly big. You can fit a lot of waste on them at any one time. You can see the grate, the waste grates here, where the waste does sit in normal operation, and you can sort of see the water tubes where energy starts to be extracted just above the combustion. And here it is in action. This is a typically what it looks like when it's operating. This is our fire. You can see that the zones very clearly, and that the front of the grate is for the burnout. So we shouldn't really get a lot of material there. We shouldn't have a lot of activity there. Should already be fully burnt out. It's just an additional stage. But yeah, you get sort of an idea of how well controlled we need the process. You can see the straight line at the back where the mainstay of the combustion stays. Steam. So I've mentioned recovery of the heat and recovery of the energy. Quite a basic process in theory. You know, there's lots of subtleties to it, but we do just take water, heat it up, take it up into its steam drum system, and we raise steam with it. You can sort of see here some of the properties of water. This is a very basic Rankine cycle. I'd say there's more subtleties to it when you look at individual plants, but yeah, we take water, it gets pumped up to the top of the boiler, it picks up all the energy through the boiler walls as it goes there. It comes out the top of the steam drum as steam. It is then further superheated, it's sent through a turbine, and then it's condensed back down to water, and the process could start again. So this water cycled through the system. We can see here the efficiency is generally between 24 and 32%. That's a function of the combustion cycle, the Rankine cycle, and the various pressures and temperatures involved in this. Here's the turbine itself. This is what extracts the energy from the steam. Steam's expanded through the turbine. Spins fast, spins at synchronous speed, and spins an electrical generator. You can see here how the steam actually comes in from the left-hand side. It expands as it goes. You see it physically expand, and the larger diameter sets of blades at the end are the end of the turbine. So it's steam comes in, expands through here, and comes out as much lower pressure steam. The bit of the turbine that spins is sometimes driven a generator directly, sometimes through a gearbox. The mechanical work, the turbines picked up from the steam, sent through a generator which spins at a synchronous speed, 50 Hertz, or some fraction thereof. It generates all our sites at 11 kV, which is a UK standard voltage. It's picked up by a transformer generally and goes off to the UK distribution networks at 33, 66 or 132 kV generally. Flue gas treatment. So I've mentioned before that our fuel we use it has all sorts of things that if we were to burn it in an uncontrolled way, in an unmonitored way, and in an unsuppressed way, could cause some serious pollutants get to the atmosphere. This is just an example of one of our systems we might use. So you see the waste, the waste is burnt in the combustion chamber. The first thing we use is an ammonia solution or similar, and that's to that's selective non-catalytic reduction. So that's to reduce the levels of NOx or nitrous oxides in the flue gas. That reacts with that to neutralize that. You can see we use a fluidized bed reactor to react lime and water in various concentrations. That is sent through the flue gas, and that any acid gases in the flue will be scrubbed out. That's sulfuric acid, hydrochloric acids that are in the gas as a result of what's gone into the front end of the process. So things like PVC plastics, plasterboard, which shouldn't be in there, but sometimes in there. Things like that will produce acid gases, and this is scrubbed out by the lime system. We then have a fabric filter. So this is the baghouse. Very basic principle of it's a physical barrier. It takes out all the fine particles of dust. They all stick to the fabric and they get knocked off into the residue chamber. What goes up the stack is monitored 24/7 by ourselves, the Environment Agency, and we have very stringent limits on all these various pollutants, and this system ensures we always meet them. I mentioned selective non-catalytic reduction. Then you can see the NOx from the waste, or from the results of the waste combustion, both fuel NOx and thermal NOx. They reacted with either ammonia or urea and water. You see the outputs of this equation, you get water and nitrogen. So we're just scrubbing down the NOx as much as we can. It's a potentially harmful gas. And you can see here the reactions that are involved in this reaction. We're just getting nitrogen and water out the end. The other one of the other things I mentioned was the acid gas scrubber. So here you can see that we've got the water and limestone, or lime, or some variant thereof, is reacted in the fluidized bed, and we get these products, which are salts that are then captured and stored in the APCR, which, if you recall from a few slides back, is then sent away. You can see a bit of a schematic of this process, but it's yeah, get the fluidized bed, it's passed through here and it's neutralized, then goes up into the baghouse as a clean gas in terms of acids and NOx, and the particulates are knocked out, scrubbed out by the baghouse. One of the consequences of historically how incinerators have been run in the distant past is that dioxins were formed. Now, dioxins do get formed from various combustion processes. We are legally obliged to run the process over 850 degrees Celsius, and quite often quite way over that. So we choose to run it quite way over that and to ensure dioxin isn't formed. We also have a activated carbon system, so any sort of dioxins that are formed, which shouldn't be there, or any trace metals that have come through as part of the waste. So we're looking at things like mercury and stuff, they're then captured by the activated carbon. You see here, we can't run without these systems. These are mandatory systems for us. And the other flue gas screen is this fabric filter, which is a basic mechanical filter. You can see here an example. I said we have some very stringent emissions limits that we must keep. Yeah, these are typical examples of what we do get on what our sites are limited to. We're looking at very, very small amounts of pollutants that we're allowed to pass through, and we do tend to usually meet these. These are stringently enforced by the EA, and we are obliged to meet them and record them. See a few more things of what we test for, and you can see that the majority are now continuous testing, so a SEM system which sits in the flue gas and monitors it 24/7. We have a few that are done as spot checks, but the vast majority are continuous. So I've given a very brief overview there of the energy from waste process as it stands. I think hopefully there's a lot of questions going to be asked at the end, and we can pick it up then if I didn't go into enough detail and stuff. This section is just looking at what assets we actually have in the UK. So in the north of the country, we have a number of sites up in Teesside. I think we've got 4 sites here in Teesside. We've got lines 1, 2, 3, 4, and 5, which are all on the same site. Here are an extension of lines 1 and 2. Was built on line 3, and then over the way we've got 4 and 5. You can see here some of the tonnages involved are quite vast. So we're looking at over 500,000 tonnes a year for Tees Valley site, nearly another 500,000 tonnes for Wilton, which is also in Teesside. It's just over the river. And then we've got a couple of smaller plants. We've got Kirklees, which deals with the local Kirklees waste in Huddersfield, and we've got the Isle of Man, which looks at all the waste from the island, and we run that with the Manx government on that one. The interesting facts are there was a film set in there, so Stormbreaker, that was filmed there. But you can see it's won architectural design awards. It's designed to look like a Viking longship. The assets we have in the south, we have you can see there we've got Sevenside Energy Recovery Centre, which takes West London waste on a rail link. We have Cornwall, which deals local Cornish waste. We have an R&D facility here, but we've got Suffolk Campus 1 Suffolk, and we've got a more novel process in Surrey Eco Park, which I will discuss a bit further later on. You can see here how we this is just the governance of how we run our various sites. We look at OEE of the sites. We look at health and safety, of course, our key priority. These are the sort of things we look at when we're comparing site to site. This is my colleagues in process engineering give me this slide. This shows how difficult it is to try and control some of our various parameters across some of our processes. We've put a lot of work into trying to find the point it normally operates at. So we're looking at very, very complex combustion control systems. We're looking at very skilled operators running these sites. We're looking at very, very intelligent engineers on the process side, looking at these processes and putting things like this in place. But you can sort of get an idea of the variation you have second by second on these sites. I did mention before the residue, which is the bottom ash that comes out. This is sent to they're now called Blue Phoenix over that, but they're a ballast company. So they convert this bottom ash to an aggregate for construction after extracting all metals we can and recycling the metals. So it's a few slides on where our latest developments are on energy from waste. Some of them are sort of what we're doing as a company. I've also put in a few of my own opinions on things. Hopefully it will provoke a lot of debate and a lot of questions. One thing that has been of great interest when I've done this talk in the past is the B project we're doing. So this project is, we're looking at installing, I say installing's probably the wrong word. We're looking at housing bees in beehives near some of our sites. the pilot project was Tees Valley, which I formerly mentioned. Obviously, we've moved it to other sites now as well. So we've got some results from Tees Valley now, which I can give you in a minute. But it's an interesting area, Tees Valley, because historically it's an area with heavy pollution going back to, well, going back 100 years really. It's an old ICI site. It's legacy of chemical industry in the area, very local area to it as well. And obviously the wider Teesside area has a lot of industry associated with it. So we were really, really interested to see what the results of this were in terms of pollutants, because we were using these bees to monitor residual pollutants that might have been in the area. We wanted to see, well, first of all, we wanted to prove that we weren't polluting the area. We know we obviously have continuous monitoring, so we were pretty confident we were, but we wanted to see what the historical impact of the pollution was in the area, if it changed over time, if any other industries nearby may be potential sources of pollution. This was something we did in partnership with a lot of our other sites nearby, because a lot of other industrial sites nearby this area as well. You can see the sort of range of the bees from this hive. It's 700 hectares. Yeah, 8 billion samples a year. This is the beauty of using animals to do your work for you. But this they bring back the pollen. Any of them could potentially be contaminated with pollutants from the surrounding area. We did some analysis of the what was brought back. When I first gave this lecture, unfortunately I didn't have any results for you, but I have got some results back. But we are looking at things historically that could have been bad, things that we now we tailor all our processes around not producing. So we've got dioxins I mentioned before, PCBs, heavy metals, which, you know, we do worry may be in waste sometimes, but we do have facilities to capture the heavy metals before they go into the air. It's just a really good indicator of the general health of the area environmental wise. This is just sort of showing how the reports come back to us, but I can give you some actual results now. So you can see here the sort of the local limits that we've set as the one in the green. We're a long way from any of them. I think we were very pleased with the results of this because, as I say, historically it's an area with a lot of pollution. A lot of these heavy metals would have been produced in the past by various companies in the chemical industry, sort of in the distant past. So you can see that some of these weren't detected at all in the natural environment. Some were detected very small amounts. I believe all of these are the highest we found was the national average. So that was a really good result. And hopefully when we carry on doing this, we'll only see these go down. So I mentioned before that I would talk around some other technologies that are being used to recover energy from waste. Now, anaerobic digestion, or AD, is one of those key ones and is a very mature technology now. It's going to become a lot more relevant because the food waste is required to be collected separately by 2023 under the English waste strategy. That's something I mentioned before. It's something that some areas now have, some areas don't. It's very patchy how it's collected between council to council. So hopefully this central government strategy will focus people's minds and get a separately collected food waste stream from every area in England. Single food waste is ideal for AD, so the anaerobic digestion, the bugs or microbes in the system break down the food waste in anaerobic fashion, which produces gas, which is mainly, I understand, methane gas. This is then piped through to a gas engine historically, and is on our site. We are commissioning on this one, but I think the way we are moving forward, and this is part of how a change in the waste industry is, we're moving towards directly injecting this into the national gas grid. And that's a technology that maybe 10 years ago we didn't quite have down, or maybe have perfected on a commercial level, but now I understand these sites are directly injecting gas produced from microbes into the gas grid from food waste. Gasification is an alternative way of breaking down municipal solid waste, other than EFW, which we talked about in the past, which is direct combustion burning. So gasification is breaking down waste using heat and limited oxygen. So we are breaking down the waste into its constituent components, and the resulting gases which produces a combustible gas. Now, at present, our site, we have raises steam from the gas, and it drives a steam turbine. The reason this technology is looked at, and the reason it has been looked at over the past few years is, number one, if we can produce a gas, we can look to increase that thermal efficiency that was mentioned before of 24 to 36%. I'm sure a lot of you are aware of combined cycle gas turbines in the power industry world, the natural gas world. They have much better thermal efficiency because they run combined cycle. So you would have the gas being run either through a gas turbine and then steam raised from the exhaust of that to run a steam turbine as well, or you could potentially look to use reciprocating engine technology. But either way, you could potentially hugely increase the efficiency using this. Again, some way down the line, but there's potential for direct grid injection of this gas into the national grid for use domestically. That's technology that's being looked at. Do we have possibly related to that is the use of this gas as a vehicle fuel, a transport fuel, as sort of an off-take. That's very related to the grid injection one. And then ultimately, I believe this is probably the way the industry is going. It's an off-take for the process industry. For example, are we going to feed this back into the hydrogen economy? It's starting to become a much bigger thing day by day. Are we going to be looking to upcycle some of the components back into the chemical industry to produce, the chemicals it came from? These are all things that are heavily being looked at the minute in the waste industry. Here's a quick aerial shot of one of our facilities, which is being commissioned at present, but we've got anaerobic digestion and gasification here. So two alternative technologies. You can see on the right hand side the tank farm here. There's a load of tanks. That's the anaerobic digester. These actually run gas engines at present, and the gas engines produce power and heat. Heat's reused in the process, and the power is exported onto the grid. You can see just some solar panels here, and then this facility to the left is the gasification facility. So this recovers energy using gasification, as I've just described. Another process we are looking at, which is related to gasification, is pyrolysis. Difference between pyrolysis and gasification is gasification takes place in low oxygen conditions. Pyrolysis is inert, so zero oxygen conditions. We've got a very interesting technique we're looking at, which is looking at breaking down plastics into a gas using pyrolysis. We have a pilot plant that's in Avonmouth, and we are looking to produce potential fuels or feedstocks for this. And so you're breaking plastic down, you reassemble its constituent parts. It's part of the circular economy. So in summary, I think that's when I started in the UK waste industry, it was very different than it is now, as there was the first sort of electrical engineer taken on by the company. We've now got a team of engineers. We work very closely with other companies. We're very heavily technical. It's night and day. It was starting to go that way already, but in the last 10 years, the pace of change has been huge. If we go back 20 years to sort of 2000, late 90s, it's even more so. Back then, we were almost entirely a landfill company with a landfill collection company with a little small portfolio of energy from waste, and now it's flipped the other way, really. Energy from waste capacity, as you saw in the chart for Suez, but it's the same across the board, across the UK. It's increased massively. massively in the last few years. So we are now sort of heading towards what the companies, things like Germany, that sort of capacity that they have. Industry continues to change at a fast pace. Yeah, it really does. I say we're looking at all these options for circular economy. We're looking at upcycling materials to be introduced back into the front end of manufacturing processes. We're looking at high grade fuels. I think this is going to come. It's going to come fast. It's certainly something that's on our radar. And I think the final point I was going to make is, you also saw in that chart before, is we need, as a residual waste, as a recovery person, as someone who works in that side of the business, we need to act in unison with the recycling, and more importantly than all, reduction in waste, because the easiest way to deal with the waste is not produce it in the first place. And I think when all these strategies work in tandem, it can work very well. Thanks for that. I'll leave. I think Rob is going to collate the questions and send them through to me. If you have any more questions, please type them in.
So, Tom, we have at this moment 26 questions. So I'm going to have a look through them and try and consolidate a few. Okay. One that's very, very quick to do is, it comes up several times, is the issue of low grade heat.
Yes.
So at the end, there's heat going up the flue stacks and whatever. What can be done to recover the sort of dregs of heat in the streams? Well,
the easiest way and one of the most cost efficient ways is something that our colleagues in Europe and our partners in Europe and elsewhere in the world do as a matter of course, which is district heating. Off-take low-grade heat people's homes, heat local industry, heat local offices. That's the easiest way. It's more a failing of the UK, I would say, rather than a technical failing. It's a political thing that needs to happen. But we do have certain sites where we have managed to get that together. So I know our site in Wilton does supply well, various grades of heat to various industrial processes in the local area. It's something we want to see more of, and it's something we need to have more of as a country, really, because it's routine in sort of northern European countries to put these systems in. Now we have another question here, which is to do with the bees. I think we should speak up for bees, which is an interesting question. Do some pollutants get released too high up for bees? So when the bees are being used as a detector, are ones that presumably lighter than disappear into the upper atmosphere and never found by the bees? Yes, they're the ones that are monitored by our continuous monitoring system. So I believe the reason we went with the bee system is because it detects the ones that may be harder to keep track of, ones where we have spot sampling and stuff rather than continuous monitoring. But essentially, I'm of the understanding that everything that comes up the stack will eventually land somewhere. So the question is more whose pollution might you be measuring if you do it local to the site. You know, it's interesting to try and detangle that, and we're very eagerly awaiting more results because there's potential for pollutants from other geographic locations. There's potential for historical ones, as I mentioned. But yeah, that's a good question. So we have an interesting question here from Martin Speed, because I think it touches on the landfill subject. Do we have the capacity in this country for no landfill? What happens in the future when we reduce waste, or why should we worry about it if we can turn it on to energy? So presumably in the end there is something that has to go to landfill. Yeah, I mean, if you look at sort of the likes of some countries which you do hear claimed quite often are zero landfill, it tends to be that they do still have a small portion of sort of hazardous waste landfills and specialist landfill sites, because there are some things that you need to basically you're storing them away underground, because I think people have an idea of landfills, and I certainly did before I started with this company, that it's a giant hole in the ground, everyone comes and just throws waste and seals it back up, but it's actually quite a intricately engineered system. It's got sort of cells, it's got gas collection, it's got leachate collection. So these sort of hazard, the more specialist landfills in particular, but all landfills generally, they have facility to sort of seal it away. So there are always going to be some things that will have to be landfill, but hopefully it's a very, very small amount in the grand scheme of the millions of tons of municipal waste that are produced.
Now, Tom, we have a good collection of questions here, and we could be here till the morning, so we're just going to pick a few more, I think, and I apologise for the people who've written some excellent questions. Well, this is an interesting operational question as an ex-operations guy. What's the operating regime for the plants like? For example, how long do they run between shutdowns? Do they run at full output or very low burn during the day?
The sites run 24/7, they base load, so it's always on basically. The shutdowns one is an interesting one. We tend to have 1 or 2 shutdowns a year. So you either go in 12 months or 6 months approximately. A lot of that depends on the regime of the plant, the age, the technology, etc., etc. But yeah, we probably are on outages more often than conventional power plants, or we certainly are, because you know, there's a certain robustness to what we burn, and it does require more maintenance on the mechanical parts in the boiler and the furnace and stuff. So yeah, but they do base load, and they do keep the output's really determined by what we get out of the waste. So it does go up and down over the day and night, but it will be determined about what's being put in, what's being delivered, rather than us sort of consciously twiddling it up and down or stuff. We try and run, we output what we can.
Right, so I think we'll go for just 2 more questions, because it's a bit demanding. One is the common theme of plastic. One question was earlier on about, do you see where we recover plastic floating in the oceans and incinerating it? And another one is to do with the pyrolysis of plastic. So do you see, because there's a sort of anxiousness of what's happening to these, the mass of plastic we use and throw away. What's the Suez, do you have a Suez view on what they might do in the future?
I mean, I know it's our head office in France is very, very heavily involved in this the plastic and oceans issue. I know that, I think I've seen them go and collect some with a very odd looking vessel and stuff. I've seen that happening in France. I think firstly we're always going to go with reduction, as I said before. So I think that's happened hugely in the last couple of years, and you know, reduction in plastic packaging generally, and plastic in particular, is something that is the first step. We can recycle what we can. Any sort of clean, high grade plastic products should be recycled and can be recycled. But you do get plastics that are degraded so much that you can't recycle them anymore through conventional methods. So I think things that we are looking down, as you mentioned, with breaking it down thermally and sort of reconstituting it, either as a fuel or potentially even as new plastic or feedstock into a different chemical process industry. These are the ways we are going to go with plastic. But I would hope we'd have a lot less going forward in the future anyway.
Right, this is the last question, because I think it's a good time to stop. We've had a very entertaining and interesting talk tonight. One is a question from Alfred Kumar, who is, does Suez buy the waste? And the question earlier on is the relative cost of the energy compared to wind power or solar. Presumably this is a 2-service activity. One is actually recovering energy from waste, but also actually processing the waste. So
yes,
it's not quite as straightforward as generating from wind power or solar.
No. If we go through the history of it, you know, back in sort of like the 60s and 70s in the UK, we had incinerators, and they weren't particularly well monitored, they weren't particularly well regulated, and they would just incinerate the waste and not recover the heat. So recovering the heat as an activity has been added on to this industry, and something that we've we've evolved and started with over time. So the economics of of energy from waste is around the waste as well as the energy. You do get gate fees for taking the waste in, as you get a gate fee for sort of landfilling waste. So any energy that's recovered as electricity is obviously part of the economic equation, but it is a recovered product rather than, I would say, rather than our mainstay of our business model.
Tom, I think the time has come to say thank you for your wonderful presentation.
Thanks a lot, Rob.
It's been really good. I've seen the odd question about CPD. If you do want a CPD certificate for attending this webinar, then please write to me, robert.mcdonald@ietvolunteer.org, and I'll organise it for you. I hope you've enjoyed it. Hope you'll join us again